Good morning, everyone. My name is Elizabeth Slate. I'm professor in the Department of Statistics at Florida State University. Welcome to the 2021 Hollander Distinguished Lecture, an annual lectureship that recognizes an internationally renowned leader and pioneering researcher in statistics who has made a sustained impact on the field. I thank all the departmental, college, and university personnel who made this event possible. I also thank the co-sponsoring societies, the American Statistical Association, the Institute for Mathematical Statistics, the National Institute for Statistical Sciences, and the Statistical Society of Canada. To initiate our proceedings, please welcome Dr. Sam Huckabee, Dean of the College of Arts and Sciences at Florida State University.
Thank you, Elizabeth, so much, and welcome everyone. It is a privilege for me to join you and make a few remarks. We're having fabulous fall weather here in Tallahassee, which is actually unusual for the month of September. So it's unfortunate that we aren't able to host this event on campus. On the other hand, we are fortunate to have technology, Zoom technology in place, so that we can have a virtual presentation of this type. We're very pleased to have with us a distinguished statistician, Dr. Susan Murphy from Harvard, to deliver today's lecture. Welcome, Dr. Murphy. Shortly, she will be formally introduced by Dr. Slate. A few words about Myles. Myles Hollander has had a long and distinguished career on the faculty here at Florida State University. He contributed to all facets of the mission of the university. This included, for example, serving as department chair twice at important times, supervising and co-supervising many graduate students, mentoring many faculty members, and really helping establish FSU statistics as a top department and centerpiece of excellence for the college and university. Myles' first-rate research and scholarship program generated many, many honors for him and recognitions over his career. I'll mention one. He was awarded a Lawton Professorship in 1998. This is the highest possible honor, internal honor that we bestow on our own faculty members. You don't get that award unless you've done it all, and Myles definitely did it all. I've known Myles for many, many years. I'm a mathematician. I met him early in my career because math and statistics interact a bit in almost every place, certainly here. And it's just a great honor for me to help kick off this year's edition of the Hollander Lecture Series. So this concludes my brief set of remarks. Thank you so much for your attention. It is my pleasure to now introduce Myles Hollander to say a few words.
Thank you, Sam, for joining us to initiate this event today. And thank you for the introduction. On behalf of the university and its statistics department, I welcome Dr. Susan Murphy. She is our distinguished lecturer. Susan is a world-renowned statistician who is Mallinckrodt Professor of Statistics and Computer Science at Harvard and Radcliffe Alumni Professor at the Radcliffe Institute, Harvard. Susan has numerous honors and recognitions. Among them, she is a 2013 MacArthur Fellow, a member of the National Academy of Sciences, and a member of the National Academy of Medicine. My colleague, Elizabeth Slate, will tell you more about Susan in a moment. Statistics is an exciting and challenging field. It has been a joy for me to have a career as a statistician. I endowed this annual series in appreciation of Florida State University, its statistics department, and the statistics profession. in my development, first as an undergraduate at Carnegie Tech, then as a graduate, that was in mathematics, then as a graduate student in statistics at Stanford, and later as a faculty member here at Florida State. I have learned a lot and been inspired by talks from eminent statisticians. It's my hope and aim that this lecture series will provide similar inspiration to our students, our faculty, and others around the world. I am so pleased that Susan Murphy is this year's speaker. She and Nancy Reed, the inaugural speaker, give this series immeasurable prestige and momentum. And for this, I am forever grateful to them. Now I turn this program over to my colleague, Elizabeth Slate. Elizabeth is a distinguished FSU research professor, and she is also the Duncan McLean and Pearl Levine Fairweather Professor of Statistics. Thank you, Elizabeth, for all you do to bring this lecture to fruition.
Thank you very much, Myles. It's my great pleasure to introduce the 2021 Hollander Distinguished Lecturer, Dr. Susan Murphy. Dr. Murphy, as Myles said, is Mallinckrodt Professor of Statistics and of Computer Science and Radcliffe Alumni Professor at the Radcliffe Institute at Harvard University. She obtained her PhD in statistics from the University of North Carolina, Chapel Hill in 1989, after a BS in mathematics from Louisiana State University. She was on the faculty at Penn State and the University of Michigan before joining Harvard in 2017. Dr. Murphy has developed groundbreaking innovations in sequential decision-making tailored to the individual. She led the development of sequential multiple assignment randomized trials, known as SMART studies, which enable comparison of treatment strategies that adapt to the individual. She is a leader in development of just-in-time adaptive interventions that use mobile sensors to optimally support individual health. Her methods are used to improve treatments in mental health, chronic diseases, addiction, autism, and many other areas. Dr. Murphy has influenced our profession not only with her research, but also as president of the Bernoulli Society, president of the Institute of Mathematical Statistics, and as editor of its flagship journal, the Annals of Statistics, and with service on committees for the National Academies and numerous advisory councils to statistical societies. Among her many professional honors are Fellow of the Institute of Mathematical Statistics, Fellow of the American Statistical Association, Fellow of the College on Problems in Drug Dependence, elected member of the International Statistical Institute. She won the Distinguished Achievement Award from COPS, that is the Committee of Past Presidents of Statistical Societies. She is a MacArthur Fellow. She won the Royal Statistical Society Guy Medal in silver. And as we've heard, she's a member of the National Academy of Medicine and a member of the National Academy of Sciences. I hope this provides a sense of the depth and impact of Dr. Murphy's contributions. During the talk, please remain on mute and enter all questions into the Zoom chat window. My colleague, Dr. Felipe Barrientos, will direct your questions to Dr. Murphy following the presentation. Please join me in welcoming Dr. Susan Murphy, whose talk is entitled, "We used a Bandit algorithm to personalize, but did it work?"
Thanks so much, Elizabeth. Let me get on the slide and fix it so I can see people's faces. Elizabeth knows I'm looking at her the whole time. It's a pleasure. It's a pleasure to be here with all of you today. You can see the first slide here. And I just want to take, my next slide is just a brief excursion to express what an honor I feel it is to be to honor Myles Hollander. Like many of you here, I'm sure you, when I was a grad student and when I was assistant professor, his book on non-parametric statistical methods, I have here the 3rd edition, but this was an earlier edition. In my case, it was the go-to book when you wanted to do anything with non-parametric statistics. So it was really great. And then when I was preparing for this talk, I thought, okay, I want to investigate Myles. And so I went back and I found 2 things I thought were really interesting. First of all, this book that's in the middle, The Statistical Exorcist, Dispelling Statistics Anxiety. I wish more of us would write books like this. This is how statisticians would be seen by the world as really reaching out to the world and be seen as the rock stars that they should be seen as. Thank you, Myles, for writing that book. This is a totally cool book. I love the title. And the second thing I realized in my investigations of Myles is that he has this paper with Etzel Pina in JASA 1988. It's the title is Non-Parametric Tests Under Restricted Treatment Assignment Rules. And at that time, there was this whole group of people who were working on adaptive clinical trials and so on. And these are very weird. Once you look at the data, after the data is collected, it's all quite odd because the data you see was informed by the data you got as you went through the study. And this is one of those papers that tried to deal with this issue. And there, in Myles' case, in Etzel's case, they developed a conditional randomization procedure so that one could do inference. But these are hard problems because the data you actually see has been impacted by the data you already saw. One could call this adaptive sampling. And indeed, most of what I talk about today is related to that, although I'm not going to touch on it directly. That's why I was so interested in that paper. So thank you, Myles, again. It's an honor. Okay, so back to the talk. This kind of work, it involves large teams, computer scientists, statisticians, human-computer interaction specialists, a whole variety of behavioral scientists. I just wanted to shout out Pedja Klashnia. He's the human-computer interaction scientist. Peng Liao, he's the person who who devised the algorithm that we're going to look at today. Kelly Zhang, a PhD student in computer science, and Zheyoung Ji, a PhD student in statistics. So what we'll do is we'll start off with, I'll describe heart steps to you. If you've heard me speak before, you know that I often use heart steps to explain a lot of the ideas. It helps me be clear. So in heart steps, it was a set of 3, all of these studies are over. The goal was, it was 3 studies were funded to develop an activity, a mobile activity coach. Each individual, each user had a tracker they would wear on their wrists that would record their step count, minute by minute step count, as well as some heart rate and some measure of sleep quality. And the idea was to conduct these 3 sets of studies to develop an app for people at high risk. And in this case, stage 1 hypertension, individuals newly diagnosed with stage 1 hypertension. And today, most of the discussion will be about the second and the third trials. And you see the words that I'm using to describe these trials. I'm using the word micro-randomized and personalized, and that should become clear as the talk proceeds, what is meant by these words. So in heart steps, this is a typical setting in which you're developing a digital app. There's usually a number of intervention components. In the case of heart steps, there was 6 intervention components, and we're going to only look at 1 of the 6. And that is these contextually tailored activity suggestions. These suggestions could be delivered to the individual. What would happen is their lock screen on their smartphone would light up, And there would be a little notification on the lock screen. And you can see an example of this on the right-hand side. This could occur at any of 5 times a day. And these were times that were user-specific times. They were about 2 to 2.5 hours related to that individual's morning, mid-afternoon, and so on. And at each time, the notification would either be delivered or not. So this contextually tailored activity suggestion would be delivered or not. And the content of the suggestion is always tailored to sensor data. So this suggestion, I got this suggestion. It was in the morning, a work day, and it was pretty cold outside. And you can see how it's trying to help me reframe it and be a little bit more active. And it's tailored to your location, time of day, weather, and so on. The outcome, which I'm going to call a reward in the future slides, and I'm going to call sending a suggestion versus not as a binary action. The outcome, this suggestion is intended to help the user in the moment. So it's a very brief, in the moment kind of outcome, the 30-minute step count after each of these 5 time points per day. So if you had a study like this and you conducted the study, what happens is the actions are being randomized. The binary actions are randomized. And so depending on the duration of the study, we have 2. In HeartSteps V2, there was 450 times that an individual could be randomized. And in V3, 1,350 times an individual could be randomized. And after the study's over, it help you see the way the data would look is on each person, you have a long stream, like a time series. And the time series is made up of tuples. And the tuples are S for state, A for action, R for reward. So state here includes their current location at that time, whether they're at home, work, or someplace else, what the weather's like, how active they've been around that time over the past week, how engaged they are with the app, are they looking at that for other reasons, and so on. And of course, step count, recent step count. Action is whether or not this suggestion is delivered or not. And then reward, we use the log of the 30-minute step count because step count is highly skewed. At the bottom of the slide, I'm going to give you my notation. So the notation here is the expected reward given current state and current action, the binary action in our case, is just denoted by lowercase r of SA. That's all. And I'm going to use this notation throughout this talk. So what I want to talk to you about is how we used a generalization of a Bandit algorithm to conduct the micro-randomizations. So we say micro-randomization because each person is randomized at micro time units many times. And we used a generalization of a Bandit algorithm to do that. This algorithm lived on the cloud, and the device would communicate back and forth with the cloud during the day. So this is a way to think about online personalization. And why do I say that? Because the algorithm is developed with the goal of maximizing the sum of step counts over the duration of that individual's study duration. Now, this area is really in its infancy because the algorithm is subject to a variety of, in the development of the algorithm, one has to take into account a variety of constraints. And at this time, at the time this algorithm was developed, and even to this day, a lot of these constraints they're not well defined. They're very qualitative. And one of the big challenges in this area is to make them more quantitative. So for example, one big constraint on the algorithm that's determining the probabilities with which a tailored activity suggestion would be sent or not, is the desire after the study's over to take those time series, one per person, and use that for what's called off-policy learning, or in the statistical community, you might want to do causal inference. These are randomized studies, so you definitely want to do some sort of causal inference after the study's over. Also, another aspect of these problems is burden on the individual. And you know this if you've ever downloaded a commercial app. Often, many commercial apps, the notifications are not personalized at all, and you tend to get them all the time. It's highly burdensome. So that's a consideration that always is in the back of the designer of the algorithm's mind. Okay, in HeartSteps V2 and V3, we generalized the Thompson sampling bandit algorithm. It's totally cool. You know, we in the biostat community, we invented the Thompson sampling algorithm like a long time ago, decades ago. And now it's one of the dominant algorithms used to decide what ads we see on like Facebook, on Google, and so on. But we in our community developed this algorithm. It's totally cool. But we want to use this now for health, to improve health. So when you look at, there's a whole variety of online decision-making algorithms, not just the Thompson sampling. And they pretty much, if they're run online as the study progresses, they pretty much always have two elements. There's always a learning algorithm, which in the world of statistics is some sort of statistical model that is incrementally updated. And then the second element is an action selection strategy. And that's how these actions are selected. So in our case, with a Thompson sampling bandit, what we use is a Bayesian linear regression model for the mean of the reward given current state and action. If you're familiar with the GP models, the Gaussian process models that are used in machine learning, this turns out to be analogous to a Gaussian process model with a very simple kernel. The nice thing about this is as you get increasing amounts of data, you can think about generalizing the Bayesian linear regression model in a really nice coherent way by going through the GP route. The action selection is what people now call posterior sampling. And so what does that mean? What it means is you use your Bayesian linear regression to calculate the posterior probability that it's better to send it, of whether or not it's better to send a message or not. So here I have the mean reward in current state. If you send an action, that's A equal 1, minus the mean reward in the current state, current location, weather, and so on. If you don't send an action, and you calculate the posterior probability of this difference, so the advantage of sending a suggestion versus not, and you calculate the probability that it exceeds some threshold. Now, in classical Thompson sampling, the threshold is 0. Here in this study, I won't go into it in detail, but we actually constructed a delayed effects term to help try and manage burden. And that term was constructed from HeartSteps V1. And the Thompson sampling, that is the posterior distribution, did not take into account any uncertainty in this threshold here. Okay. So what we're going to do is in the action selection is we're going to determine that posterior probability that the advantage of sending a suggestion versus not is greater than the threshold for that particular state. We'll take that posterior probability and then we randomize to sending a suggestion with that posterior probability. That's what we mean by posterior sampling. First, you calculate the posterior probability, then you use it as a randomization probability. I just want to make, I'm not going to go through all the ways in which we altered Thompson sampling, but I just want to talk about just a couple of considerations that arose. First of all, we because of the high noise in these settings, we had to be very careful with the number of coefficients we would try to estimate. And so what we did was we constructed a low dimensional model of the advantage of sending a suggestion versus not. This theta is only 5-dimensional. The first entry in theta corresponds to an average overall effect of sending a suggestion versus not. And then the remaining 4 entries have to do with particular features, one of which is the individual's current location. Another is how active the person has been around that same time. We're going to see a list of the features in a further slides. The next thing we did, again, because of the incredible noise in this type of setting. Remember, you're experimenting as someone goes about their life. So there's a great deal of noise. As we constructed an informative prior. In fact, all the studies we're now working on, I only do informative priors. I've drank that Kool-Aid. In terms of developing an algorithm, an online decision-making algorithm, informative priors is a great way to initialize. So the prior here was a Gaussian prior for that 5-dimensional theta. And the most important thing for us to take forward into the next slides is the fact that the first entry in theta, these were all constructed using Hartsteps v1. In Hartsteps v1, there was a really strong effect of sending a suggestion versus not on people's 30-minute step count. So that first entry in theta, it has a prior mean, which is positive. It's like 0.47. All of the other prior means are 0, okay? The prior variances are also informed by Hartsteps v1. We'll talk about this later. So this is how the algorithm gets initialized, is via this prior. Okay, so now I want to talk just a little bit about the action selection strategy. This is this posterior sampling. So we're going to randomize to send a suggestion. The algorithm is going to randomize to send a suggestion with this posterior probability that the advantage of sending a suggestion versus not exceeds this threshold. And so what happens is in some states, say like in the morning on the weekdays, one might see that the posterior distribution of the advantage minus the threshold centers around 0, indicating there's just not a lot of evidence so far in the data that it's worthwhile to send a suggestion. Yet posterior sampling is going to sample with a probability averaging around 0.5. Is this a good idea? Does this even make sense? No. You don't want to send suggestions. When you don't currently have a lot of evidence that a suggestion is good, you don't want to send it half the time. And in other states, the posterior, the Gaussian distribution of the advantage sending a suggestion versus not minus the threshold will be peaked and will center around a positive mean, much larger than 0, indicating that the accruing evidence indicates that that individual in that state is highly responsive. The posterior probability then will be close to 1. Do we want to do that? So if we find that in the morning on the weekends, an individual appears to be highly responsive, do we want to almost always send a message in the morning on the weekends? No. No. And the third issue that comes up is we have to be able to do analyses of the data after that. We have to learn between these studies as well. We have to permit causal inferences as well as off-policy learning, that is learning other types of ways to assign sending suggestions after the end of the data collection. If during the collection of the data, we choose sending an action in a particular state with probability 0, that is, we never send a suggestion in a particular state, then after the study's over, we cannot learn whether or not it was useful to do that. Yeah. So we have to, again, we have to do some engineering. So what you're seeing me do is be an engineer in the sense that I'm having to deal with the real problems in front of me. And the open question is, how do you do this all in a principled way? So here's what we did. What we did was we used this little blue curve that I drew here. So the x-axis is the posterior probability. So you can see I put 0.5 and 0.8. And the y-axis is the probability that the algorithm actually used in randomizing to send a suggestion. So if the posterior probability was around 0.5, indicating not much evidence, the algorithm sent the suggestion with probability 0.2. If the posterior probability was like 0.9 or higher than 0.8, the algorithm sent the suggestion with probability 0.8. And you can, at the bottom of the slide, you can see the rationales for this. Now, these numbers, 0.8 and 0.2, they're determined by a team, a clinical science team. So there was this big discussion about, well, how often do we want to send a suggestion in a particular state in which it looks like the suggestion is really useful? And we said, okay, around 80% of the time, max. And then with the 0.2, that came about, we're really concerned about, well, if the suggestion does not appear very useful, do we want to go down to 0, for example? And there is this, it's understood in this field, in behavioral science, in psychology, that randomness itself has a therapeutic effect. It's more engaging. You become less habituated. And so, and also we need to do we need to learn after the study's over. So we said, okay, if there's not a lot of evidence, we'll send the message 20% of the time. Oh, I have to pause for a clarifying question. Felipe.
Yes, Dr. Murphy, we have a question by Swan Lee. I apologize if I'm saying your name incorrectly. The question says, is maximizing the sum of rewards over a period of time a different problem than maximizing the reward at each point in time?
It is. So having an algorithm that attempts to maximize the sum of the rewards, what it's trying to do is learn, in our case, we could say personalize as fast as possible. This algorithm does focus, for example, an oracle would know what the reward function is and would use that reward function at each time to decide whether or not to send a suggestion. And so that an oracle would both maximize the reward at that time as well as the sum of the rewards. So the maximization of the sum of the rewards is about learning fast learning of how to maximize the reward at any given time. Both of these problems, the second problem, maximizing the sum, the optimal solution is a dynamic programming problem. And what's great about Thompson sampling is it's a computationally stable way to try to approximate the solution to learning fast over time, for a sum of rewards. These are problems that they're NP hard. They're not possible really to solve. So one is always looking for approximations. And in fact, Thompson sampling in many settings achieves the fastest learning rate. The first order rate is the fastest, is as fast as one would expect to get. Okay, Philippe, I'll go on.
There is one more.
Okay.
So do you decide the threshold delta S delay effect bias term? And how does it affect the TS behavior?
Right. So that threshold, what we did was we built we used HeartSteps V1, the prior study, and we built a Markov decision process using HeartSteps V1. And we know that if you really have delayed effects, you shouldn't be targeting just the current reward. You should target the maximization of the current reward plus the value of the next state. The value of the next state is the expectation of the sum of the future rewards given the next state. And that delta function, that bias term, it's a proxy that we built using HeartSteps V1 for the value of next state. So we're engineering the current reward step count, 30-minute step count, by adding a proxy for the value of next state. And if in a full MDP, one would learn that online, that value of next state at the same time. These problems are so noisy, and the value of next state is very hard to estimate. So we just learned that across people with HeartSteps V1, and we just used it.
Okay, thank you, Dr. Murphy, for answering these questions. Yeah, there are no more clarification questions.
Okay, great. Okay, so we're going to go on. Okay. So what happened in this V2 and V3 is the HeartSteps ran this online Bandit algorithm separately on each individual. N is 91 here, about half from V2 and half from V3. And so the study ends, and there's some questions that arise. Now, we actually, in other work, we've developed primary analyses for these studies. So this is not what this is about. This is more about taking a deep dive and looking at the problem and asking ourselves, did personalization occur? Did the algorithm learn quickly for each individual, or for some individuals, in which settings it should send a suggestion, in which settings it should not? And so right now we're going to assume we're in a Bandit type setting. That is that we've captured all the delayed effects with our threshold. We don't have to worry about them anymore. So the first question we ask is, well, on average, across, is it useful to send this suggestion or not? Across all contexts, across all users, is it even useful? Another question we might ask is the better action I send a suggestion versus not? Is that user specific? Or is it that everyone in the morning on weekdays does better and everyone in the morning on weekends does not, for example? So when we first started posing these questions, we just didn't know what we didn't know what literature to even try to appeal to. And what we ended up doing was we used ideas from classical meta-analysis. And if you're familiar with meta-analyses, this is an extremely mature area of statistics. In fact, the tutorial at the bottom of the slide, this is a lovely tutorial. That was when the field was pretty mature, 22 years ago. And so the idea here in meta-analyses is you're combining results across multiple clinical trials. That's classical meta-analysis. Is you have multiple clinical trials of different chemotherapies, for example, and you want to combine your results across those trials and make some overall statements. So here, what we're going to do is we're going to act as if each user is a trial. And on each user, we repeatedly experimented. So each user is like a study. So we denote each user's vector, 5-dimensional vector of treatment coefficients by theta sub 0i. We don't know this. This is unknown. That belongs to the ith user. Then what we do is we estimate the ith user's treatment effect coefficients by the vector of posterior means. Now, this is a Gaussian linear regression. So all it is ridge regression. So we use a ridge regression to estimate theta 0 sub I for the ith user, right? And we call it theta hat I. And remember, the thetas are the weights and the advantage of sending a suggestion. This is the reward in state S of sending a suggestion for the ith person minus the reward in state S of not sending a suggestion. So in classical meta-analysis, it's really interesting. There's two ways that people generally think. First of all, they may focus just on the clinical trials in front of them. In our case, just the users in front of us, 91 users. And you only want to make inference about those 91 trials, those 91 users. In that case, the approximation is that your ridge regression estimator has an approximate normal distribution with the underlying user-specific 5-dimensional vector of coefficients, and then some variance covariance due to the fact that you only observe the user for a certain period of time. The second way to think is population level inference. So now we think of those 91, in our case, 91 users, 91 trials, as being drawn from a superpopulation of users. And actually, in our setting, this makes a lot of sense. All of these studies went on at Kaiser in Seattle. The individuals were, as soon as they were diagnosed with stage 1 hypertension, they were then asked, do you want to get into this study? So for example, if Kaiser is thinking about rolling out activity coach for their patients who are newly diagnosed with stage 1 hypertension, they might be interested in population inference. In this case, one makes an additional assumption, and that it's multi-level type assumption that each user's treatment effects, they're randomly sampled with the overall mean across all population of individuals with stage 1 hypertension at Kaiser having some mean theta pop, that's a 5-dimensional vector of regression coefficients, and then some variance covariance, which measures the variation across individuals in that population. So there's the two ways to think about inference: population level and finite sample. Okay, so first we're going to do population. So what I'm going to do is I'm going to just take those statistical methods straight out of meta-analysis. And so the first thing is to ask, well, is there evidence? This is the question, the first question I posed on a prior slide. Is there evidence on average if it's worthwhile to send a suggestion versus not? The estimator is a weighted average here. And so this E is a one-hot vector. All it does is it's a vector of zeros with 1, 1, and it's just picking out each theta in turn, each of the 5 thetas in turn. And you get a weighted average. You need to get a weighted average because each individual has a differing amount of information, differing number of trials. So you have to weight it. And the weights are both the covariance of variation within an individual as well as a variation between individuals. We use a robust standard error for the first, and for the second, we use empirical Bayes method. So I just want to talk just a little bit about this green table. You can see the 4 features. One is the prior number of time, prior dosage, how much that person is being pinged for all of the different components of this intervention, the Heart Steps intervention, whether or not the person, this engagement, whether or not they were accessing the app, their current location, and how variable their activity was around that same time over the prior week. And at first, the whole team, we look at this and we think, oh man, this is fantastic. This high noise setting, we're seeing on average, the overall effect confidence interval, this frequentist analysis, doesn't contain 0, we feel really good. But then you look at the second row and you don't feel good anymore. Because the second row indicates that the effect of the interaction effect of dosage, which is what we anticipated would be negative. The more you've been bothering that person, the less responsive they're going to be. And that confidence interval, again, doesn't contain 0, but that effect is estimated to be pretty large. This pretty much kills. And if the person has had very many suggestions, on average across the population, remember this is population level inference. On average, if individuals have received very many messages, nothing is going on. And the next slide makes that really clear. So here we're looking at a particular state. They've had an average number of messages. They're currently engaged. They're looking at the app of their own volition. They're at home or work, so in a structured environment. And the recent variability in their activity around that time over the prior week is low. And we get the confidence interval. The dosage kills it. kills it. So on average, across the population, the data indicates there's very little going on. The only time you get an effect is if you keep the prior dosage very low, that you see any evidence. Then you ask, well, does this depend on the individual? Now we go to finite sample inference. So our 91 clinical trials on 91 individuals, we're only interested in them and no one else. And they have multiple randomizations per trial, right? Per individual. And here is a chi-squared test statistic. Again, it comes straight out of meta-analysis. You're using the weights. Here you only weight, because it's a finite sample analysis, you only weight by the within-person variance. And you compare this to a chi-squared on 91 minus 1 degrees of freedom. Remember, E is just picking out each of the 5 entries one by one. Here's the results. It's pretty strong. Lots of variation between users. Lots of variation. So lots of variation between the clinical trials in terms of the effect of each one of these different coefficients. Okay, so then the next question we asked, on average, does the Bandit algorithm, so this is across the population, is it learning? Is it doing better than the prior? Because what we could have done was taken Hartstepp's V1, built that prior, and just use that to select, use that to randomize during the entire study. So is the Bandit, in some sense, learning? And now this is learning at the population level, not at the 91 user level, but at the population level. That's what this question's about. So the way one looks at that is by the average reward. And so here at the bottom of the slide on the left-hand side, you see this is the average reward is the average of the ith person's expected reward in states and under the policy, pi. Pi is the prior policy built from the prior distribution. So that expectation out here, this is not averaging over people. It's averaging over the states that individual finds themselves in, as well as the posterior sampling done by the Thompson sampling algorithm. Those are the two things that expectation averages over. So we want to, again, the question is, did the Bandit do better than if we just stuck with the prior and run the study? So the Bandit, I'm going to call its approach, its posterior sampling approach. I'll denote that by B for Bandit. It has a posterior sampling probability at each time. And of course, there the average reward is just the average reward that you saw on that individual. And then for the prior, what we do is an importance sampling estimator. With the denominator being the prior probabilities, and the numerator, the Bandit probabilities, and the numerator being the prior probabilities. There's actually better ways to estimate this average reward here. We just went with this one for this example. Okay, so now when I go to classical meta-analysis, theta is just one-dimensional. So each individual's theta 0I is just the value under the Bandit policy, the Bandit algorithm, minus the value if we just use the prior, built off of a prior study. And theta hat I is just that scalar. It's just the estimated average rewards under the Bandit algorithm minus the average rewards we would have gotten had we used the prior. And here we're going to assume on average, it has a normal, this difference has a normal distribution, and we have the multi-level, the higher hierarchical level, so that the average from one person to the next is normally distributed across the population. Again, we just use classical meta-analyses for this. And the confidence intervals are quite interesting. So The first confidence interval is, I mean, it's barely, but it doesn't contain 0. And the conclusion is, remember the prior? In Hartsoft's V1, there was strong evidence on average across everyone that sending a suggestion was better than not. So if you had used the prior here, you'd be sending a lot of suggestions, a lot more suggestions. Whereas the Bandit doesn't do that, it backs off. That's what's happening here. That's what we think is happening. And then we also asked, well, does this difference, we did a hypothesis test, that's the test at the bottom of the slide. Does this difference in value, does it vary from one individual to the next? And that test statistic is, is compared to a chi-squared on 90 degrees. It's highly significant, indicating lots of variability. I have 2 more questions I want to ask, and these actually were the questions that motivated this entire effort. In fact, the most interesting one is this question 7, but it's good to think about 6 because it helps you get to 7. So we'll go to 6, and now we're just doing exploratory. Everything we've done is essentially exploratory. It's not primary data analyses or anything like that that one would use in these types of studies, but these are our EDA. So on average across users, does it appear that the Bandit algorithm learns across time? Now, the analyses we've already looked at so far indicate that on average across individuals, as soon as you have any kind of reasonable dose, you don't see much of an effect of sending a suggestion, remember? But the prior said, yes, there was going to be a big effect. So this question number 6 is really, did the Bandit algorithm, how fast did it learn that that prior was wrong? How fast? Okay, so the way we do this is with a bootstrap. So, okay, so we're going to focus on the figure on the left first. I'll only talk about the figure on the left side first. So the blue curve is the actual data. It's the average across the 91 individuals of the posterior mean of the treatment effect in this particular state. You see the state here. It's when the person has had an average dosage, they're engaged, homework, and so on. So in that state, what is the average treatment effect across the 91 users? That's what that blue curve is. And if you look closely at the blue curve, at the very beginning, the blue dot is at 0.47. That's the prior mean. In fact, all of these black curves, of which there are 2,000, every single curve is initialized by the prior mean, right? So all the black curves, the blue curve, everything starts at 0.47. And then you see this average, it deteriorates really fast. Like within, say, I don't know, 20, 21, 25 days, yeah, it's learned. Okay, so what are the black curves? There's 2,000 black curves. Each black curve is applying the Bandit to a bootstrap sample of users. So I'm going to explain what I mean by that. So first you take the 91 users, and we use the posterior the posterior mean, and we subtracted from their step counts, the log of their step count, their 30-minute step counts. We subtracted our estimated regression function. We get a residual. So now on each user, we have state residual, state residual, state residual across the entire time that user's in the study. We have 91 series like this, one per user. We get a bootstrap sample of these 91 series. Then we run the Bandit algorithm under the scenario that a particular thing is true. And we ran it under the scenario that the prior was correct. The prior mean values were correct. So like whenever the Bandit said, send a suggestion, then we would add back to the residual the regression that's associated with sending a suggestion if the prior was correct, and so on. So every black line is an average across those 91 bootstrapped individuals, each of which had a Bandit algorithm run on it. And you can see that if the prior were true, the math stays way above. So here, what we get from this, what message do I get from this? Is that indeed, yes, the algorithm learned very quickly that the prior was not correct. Now, on the right-hand side, the figure on the right-hand side was sort of like a smell test. We wanted to just make sure things were working the way we thought they should. So here we did the exact same thing, but now we did it under the truth that the posterior for each individual is the correct. Those are the correct regression coefficients. And there you see the mass of all the 2,000 studies, the blue curve stays well within that mass. So it's all coherent. Okay, it's very interesting. So that's good. The next question, this question is the most interesting question for me personally. It's the last thing we're going to talk about today. And this is the most disturbing question of all, too. We all know about how AI, there's all this misuse of AI in our society right now. And we all know that you can get phenomenal results just by accident because of stochasticity. So what happens in a study like this is you look at some individuals and you find just phenomenal results. You just love it. And I'll show you one. Okay, here was an individual in V3. I'll talk to you about the figure first. So the horizontal axis is the day in the study. So this individual came into the study in mid-November 2019 and left the study at the beginning of August in 2020. That means this individual was in the study during through the study before COVID and after the onset. In fact, they're in Seattle because this is where the studies run, and the Seattle shut down in March. So you can see how the curve looks a little different during that period of the COVID shutdown. So the y-axis, the height of the dot on the y-axis corresponds to the posterior mean in the person's current state on that day, divided by their posterior standard deviation of the treatment effect in the person's current state on that day. This is just one individual. So it's like a standardized treatment effect. And so each dot, this individual is relatively, a lot of the dots are greater than 0. So the algorithm is repeatedly predicting that sending a suggestion is better than not. That's what the algorithm is doing. Indeed, if you color code the dots, you realize that all the dots that are all higher are dots that the individual at this time appears to be engaged. They're looking at the app of their own volition. That's the blue dots. The red dots are when they're not doing that. So I show this to a behavioral scientist, one of my colleagues. And what do we immediately want to do? The conclusion we want to make is, man, this is phenomenal. We are personalizing because the probability with which they're going to get a suggestion depends on the height of these dots. It depends on the estimated treatment effect. This is fantastic. I mean, it just sounds glorious. So the question as a statistician is, we used a stochastic algorithm. We used posterior sampling. Is this just stochasticity, right? Okay. So we did another bootstrap study. Here, the blue curve it's about the interaction of engagement. So it's all examining the effect of engagement, because that's what that last figure told us, is engagement is really important. If they're engaged, you should send a message. If they're not, you shouldn't. So the blue curve and the prior mean coefficient for engagement was 0. And that's why that blue curve starts at 0. And you can see the individual's blue curve over time. Each of the 2,000 black curves are a bootstrapped version of that individual, this one individual. And here what we're doing is we're sampling residuals within that individual and then running the Bandit. It's very interesting because if I had been left to my own devices, I would have said, well, already by late December or so, we have pretty good evidence that you should send a suggestion when the person is currently engaged versus not. But I go to this thing and I realize, no, so these black curves, they were all generated under the ground truth that there's no effective engagement. So at the beginning, the blue curve is well within that ground truth. So even though it just looks totally wonderful here, and you think personalization, no, it's not true. At least according to this exploratory data analysis. Now, if you get to the end of the study, there the blue curve is really starting to drift to the large higher up. And you think, well, maybe there is some beginning evidence that we have an effect. Okay, last slide. So we used a sequential decision-making algorithm in an effort to personalize. So we're both learning within a person and learning across people after the study's over, doing both types of learning. But are we achieving personalized digital health? The first thing we did was we acted as if each person was sort of like a clinical trial. This assumption is fallacious. But even if you were willing to assume this, how would you do a better job? That's the first question. The second question is, how do you address assessing personalization if you realize that people's step counts across time are probably correlated? They're not that correlated actually in this particular case, but in our other studies, we get a lot of correlation. So this assumption is violated in general. How do you do it there? It's a completely open area. How do we do truth in advertising when we use an AI algorithm to personalize? Thank you.
Thank you. Wow. What a stimulating talk. Thank you very much, Dr.
Thanks.
Murphy. So Felipe Barrientos will field us questions from the audience now for some period of time.
Okay, thank you very much, Dr. Murphy, for this amazing presentation. So now Dr. Murphy will answer some questions. So I invite the audience to submit their questions by writing them here in the chat. So we already have some questions. So I will proceed to read them in order as they were submitted. So the first one is from Jairo Peña. He asked, could the rewards be highly dependent on past values?
You mean there's correlation within a person across time and rewards? I think that's what we're saying. And in this case, actually, you would have thought, the problem is this is only 30 minutes of step count, and we're only getting that every 2 to 2.5 hours. Turns out, I thought they would be really highly correlated, but we didn't see that much evidence. It was a little surprising, to be honest. I think in our other studies, where the rewards are the reward is is collected over the entire duration from one time point to the next, we see a lot more evidence of that correlation.
Okay, so we have another question by Xuan Lee. Can the phenomenal results for that individual be non-causal? She tended to look at the phone whenever he started to walk outside.
I think we got to say the whole thing again. I don't understand the question. Maybe.
Can the phenomenal results for that individual be non-causal? She tend to look at the phone whenever he started to walk outside.
Yeah, that notification disappears pretty fast because it's only really actionable in your current location with the current weather. And so there was a lot of concern about leaving the notification around for the person to see over a longer period of time because it's not, remember the context of the message is tailored to where the person is now. So they would have to act, so like if they started, I guess if, wait, let's take a scenario. Suppose the person really loves this app. And at those 5 times a day, that person's 5 times a day, they start walking. Then we're not going to see an effect because they'll be walking if we send a message and they'll be walking if we didn't send a message, right? Remember, the contrast is between when they got a message versus when they didn't. So if they're currently walking, we're not going to see an effect.
Okay, so while the audience writes their more questions, maybe I would like to ask a quick one. So can you comment on the privacy concerns or regulation that you have to deal with when you are collecting this type of data? At some point, let's say, are you allowed, maybe you are not allowed to collect the reward and you have to like somehow add some noise to it?
Yeah, so in this setting, I said we collected location, but we didn't collect GPS. So on the phone, the GPS was immediately categorized, the GPS signal was categorized as home, work, or other. And then the GPS was discarded. And we don't know where home is. I mean, home is just home. Like we don't have the person's address. Like the data sets I have doesn't have the person's address. It doesn't have their work address. I just know home, work, or other. So that's one way that you, there is a lot of processing that's done on the phone where you create features and only those features get sent to the cloud. You don't, in other words, you don't send GPS traces to the cloud. You send the feature home, work, or other to the cloud. And home, no one knows what home, home, we don't know the address of the home. All these transmissions have to be HIPAA compliant. So they all have to be encoded, so there's a lot of security issues in terms of data storage, particularly with this real-time transmission of data from the phone, any data on the phone, how it's being stored momentarily on the phone, how it's sent to the cloud, and so on. That all has to be handled very carefully. I have been involved in studies in drug use, and there it's very tricky. People often think, oh, well, let's just not send data to the cloud, and it's much better for the individual. Well, in drug use, that's not the case. If you ask someone about their current use of drugs, this is mostly illicit drugs, you want to get that information off their phone as soon as possible, because if they end up in a run-in with the law, someone could potentially get the information off their phone. So depending on the actual circumstances, you either want to get information that's collected from the individual really quickly off the phone, or you don't want to send it to the cloud. It just depends on the kind of information and the setting. But all of these considerations enter in this type of a problem. This is one of the reasons why you need such big teams.
Yeah. Okay, thank you. The following questions come from William Farr. He said, interesting talk, thanks. Did the COVID environment have a major effect? People might not want to take action that involve going outside. Activities would be limited by the COVID environment. I know I was very inactive because of it. Do you have plans to do the analysis once the pandemic is over?
Well, this study is over now, so there's no more data collection on any of these individuals. And we already saw with this one user that during the shutdown of Seattle, this person clearly, I mean, the predictions kept saying you're not going to see much an effect of sending a suggestion during that March period, that late March period. But, right after that, we started getting the message that we need to go outside because it's safer. And you can kind of see that from this. This is just one individual, I realize, a sample of one, but you see the COVID pattern very clearly on this one individual. In general, across the people, we haven't looked. We haven't also looked at baseline data, because I think it'll be interesting to see if, for example, individuals who have comorbid conditions besides stage 1 hypertension respond differently from individuals that don't. And also, is there a different signal for the responsivity during the shutdown, the initial shutdown? I mean, that's when the shock really occurs, right? We haven't done any of that. I mean, there's just so much we can do that we haven't done. These data sets are incredibly rich data sets.
We have 5 minutes before the end of the Q&A session. So if you would like to ask a question, please add it in the chat. So this question is by Bill Salokar. Do you see applications of this in the shopping setting, where retailers or manufacturers send messaging to prompt purchases? Is this what Waze uses to send me messages about fast food, gas, etc.?
My understanding is the current state of the art. Now, I'm not talking about internet, ads on the internet, okay? There, the state of the art is extremely high. There's a lot of personalization going on. But in terms of apps, my understanding is we're still pretty primitive. And if you download a lot of these apps, you'll know exactly what I'm talking about. Like, for example, a lot of the apps that are for activity suggestions, they'll send you messages just over and over and over again. So I could imagine, you know, I don't know if Waze is using some sort of online decision, you know, personalization type algorithm or not. I would suspect it's right now, it's probably they form the decision rules themselves. For example, here's an example. When the individual is within X meters of where they normally, of a fast food place that's paid us money to advertise, we send a message. That would be how I would expect most. So expert systems. I think right now, most commercial apps that are sent to individuals, you know, mobile apps, are more expert systems. But it is, I mean, it is alarming. On the other hand, like with Heart Steps, we allowed the user to turn off the app. You know, because we need therapeutic alliance. I can't remember the word, but we need the person to want to value our offer. So we had to permit a lot of agency on the, I mean, you have to allow the individual, it has to be the individual's choice at the end of the day. And we respect it. I mean, the behavioral science teams respect that a great deal. Now, with these shopping settings, that's a different ballgame, right? You have to think of what's the utility function for the, you know, for Waze. They're going to only start to really try and personalize if you delete the Waze app in response to being bothered too much.
This is a question by Dr. Elizabeth Slate. So would you additionally comment on the tension between the need to collect data in sparse regions where the movement toward higher reward seems unlikely versus the goal of maximizing the reward? Would the utility function vary by context, strength of prior information, etc.?
Thanks, Elizabeth. That's a great question. So that's the exploration versus exploitation conflict, right? And that's what posterior sampling is so nice about. I mean, it's not the optimal approach to balance. So okay, exploration is the need to collect data in sparse regions so as to get a better estimator, to make the posterior distribution concentrate better. Exploitation in this context means using the current posterior means just to choose a treatment, the treatment that looks best at this time. And so when you say, I want to develop an algorithm to maximize the sum of rewards online, you're talking about an algorithm that has the goal of balancing exploration and exploitation. That's what you're talking about. And posterior sampling is like a poor man's effort, because the great thing about posterior sampling is it's incorporating the posterior variance, which is your uncertainty in that state, right? And the higher the posterior variance is, the probability gets shrunk more to half. Well, in our case, it's 0.2 because we don't want to overtreat people, but you get the drift. Yeah, that's a great question.
Sorry. Okay, well, this concludes the Q&A portion of the event. Dr. Murphy, thank you very much for answering all these questions. And I will now turn it to Dr. Slate for concluding remarks.
Thank you, Susan. Fabulous talk. We really enjoyed it, and we're so happy to recognize you as a 2021 Hollander Distinguished Lecturer. Thank you for joining us this morning.
Thanks. And again, Myles, it's a great honor. I really appreciate it.